students, we were talking yesterday about inter versus intramolecular forces. And intramolecular forces are what we've discussed in the past last semester with our ionic bonds and our covalent bonds, because intramolecular forces are those bonds, what we can find in the molecule itself. But have you ever had any of these burning questions, like why some things are solid at room temperature and some things are liquids or gases? Or why some solids can dissolve in water but other solids can't? What about why some things have really low boiling points and some other things have really high boiling points? Well, all of that can be answered based on the strength of the intermolecular forces in these different substances. So that's what we're going to explore today. Now, with ionic compounds, where there's a metal and a nonmetal, there's no other intermolecular force that's present. It's just the ionic bond that's holding those substances together. And I want to remind you that the ionic bond is stronger than any kind of covalent intermolecular force. Now with covalent molecules, because we can have polar molecules and nonpolar molecules, there are other types of intermolecular forces that are going to exist between the molecules. Remember, the intermolecular forces are those that exist between the molecules themselves, not within the molecule. So there's going to be three different types of intermolecular forces that can be found between covalent molecules. The weakest of the three is going to be your London dispersion forces. Then you have your dipole-dipole interactions, and then you have hydrogen bonding. Now, of the three, hydrogen bonding is the strongest that's found between covalent molecules. It's still not stronger than ionic compounds, though. Now, these are all intermolecular forces. So in order to actually see that intermolecular force in a drawing, you would have to draw at least two molecules to visualize what's happening between those two molecules. And we'll discuss that as we go. So first, let's talk about the weakest London dispersion force. These are the weakest intermolecular forces that you can find in covalent molecules. Now, these types of forces are going to be found between nonpolar molecules, and here's why. We know that nonpolar means that the electrons are shared equally. Okay, the electrons are shared equally. So for example, if we have methane, which is CH4, we know that this is a nonpolar molecule because all of the ends are the same. There's an equal balance of electrons amongst all of those bonds. Well, we also know that electrons are constantly moving. So as these electrons move, they create this temporary imbalance of charge within the molecule. So that's why these London dispersion forces are the weakest, because it's forming a temporary dipole. We don't have any dipoles drawn on this molecule of methane here. So if we had another molecule of methane, as these molecules were moving past each other, they could form, this is a hydrogen down here, I just can't draw it. They would form this temporary attraction between these two, and this temporary attraction right here is a London dispersion force. We abbreviate that as an LDF, okay? Now, these are temporary because the electrons are constantly moving. As the electrons move, this London dispersion force that I just drew down here is going to be, taken away. It's not always going to be there as those electrons constantly move. And those London dispersion forces can then pop up and attract to another nearby methane molecule, okay? So what we want to make sure we do is draw our molecules in order to determine if these molecules are polar or nonpolar, because we're going to see these London dispersion forces in nonpolar atoms and molecules. Okay, not bond polarity, it's about the molecular polarity. All right. So let's talk more about these temporary dipoles. Like I was saying, these exist because of the movement of electrons. Now, when you have a chance, I want you to pull up the PowerPoint in Schoology, and I want you to watch this simulation. The simulation will show you how those electrons are moving and reforming these temporary dipoles throughout the atom and molecule. Now, this picture over here on the right-hand side, this one over here, you can see that it's created this temporary imbalance of electrons because you have more electrons over here on this side, creating this temporary negative dipole. And it's negative because electrons are negative. Well, as these electrons move, it can influence the electrons to move on this molecule over here to create that temporary attraction. So it could force the electrons to move over onto this side so that it can create a positive dipole and a negative dipole on this side, so we can have a temporary attraction here. So London dispersion forces are the weakest because they are just temporary. So let's practice. It says, under similar conditions, London dispersion forces are strongest in which of the following samples? Now, I forgot to talk about something, so let me go back here really quick. Okay, right up here, it says dispersion forces usually increase when more electrons are present. That's important when you're comparing nonpolar molecules or nonpolar atoms. They're weakest, or they're strongest when more electrons are present because, like I was saying, electrons are constantly moving. So if these electrons are moving and you have more electrons that are moving, you're able to form more of these temporary connections. And that's why the London dispersion forces are stronger when there's more electrons present. So let's go back to this question now. You'll notice that out of these choices, these are all noble gases. And you might think to yourself, well, Miss Welch, a helium atom doesn't have an LDF. And that's true. One helium atom does not have LDF. But if that helium came across another nearby helium atom, it could form a temporary attraction between the two, and that would be an LDF because it's between two of the same atoms, okay? These are not in the same molecule, it's between the molecules, it's between the atoms here, and it's just temporary, which is why it's LDF. Now, since all of these are noble gases, we're going to be looking to see which one has the most electrons, and that would be the strongest LDF. And that's why our answer is D. Next, we're going to discuss dipole-dipole forces. Now, London dispersion forces were the weakest because they were just temporary dipoles. Dipole-dipole forces are stronger than that because they already have these dipoles that are present. And those dipoles are permanent. Now, we talked about those dipoles yesterday. The dipoles are there because the bond is polar, okay? The element in the bond that is more electronegative is going to get the negative dipole, the sulfur in this case. The one that is least electronegative is going to get the positive dipole, and that's going to be the hydrogen. Now, we're going to base that electronegativity on the trend that increases up and to the right. Okay, this is our electronegativity trend, like we talked about. Okay. Now in this picture here, let me just zoom in for a second. This here represents a bond because it's in the molecule itself. Now this is going to be a polar covalent bond because it is between two nonmetals, so it has to be covalent, and then it's not carbon-hydrogen, and it's not bonded to itself, which means that this is a polar covalent bond. This dashed line here, that represents some kind of intermolecular force, because you can see that it is existing between this H2S molecule and this H2S molecule. Now you can see that this attraction is between a positive dipole of one molecule and the negative dipole of the other molecule. So this is a dipole-dipole interaction because it exists between polar molecules. Okay, so this right here, the fact that these are polar molecules, it what makes this the dipole-dipole interactions. LDFs can only exist between two nonpolar molecules. Dipole-dipole interactions are going to exist between two polar molecules. So it's going to be really important to draw your structure, see if there's lone pairs on that central atom, see if there's different ends, so you can actually correctly identify whether or not the substance is polar or if it's nonpolar, okay? So this shows you a little bit closer look of those dipoles in action. Remember, these dipoles are going to be a partially positive or a partially negative end based on the electron movement And you can see that the dipole-dipole interaction exists, like I said before, between a positive end of one molecule and a negative end of the other molecule. So let's practice. Which of these would experience dipole-dipole interactions between like molecules? So like I've said before, dipole-dipole interactions are going to be found between two polar molecules. So you have to draw the molecules to see if these are polar or non-polar. So I'm going to draw these molecules really quick. If you need practice drawing, pause the video, practice drawing them for yourself, and then restart to check my work. Okay, but I'll just pop these up really quick. So here's carbon dioxide. Here's PF3, which we did yesterday in our notes. And then SO3. It's a little sloppy, sorry. And then I'm going to put CH3 up here in the corner, which we also did yesterday in our notes. So we have to decide if each of these is going to be polar or non-polar. So let's look at the CO2, okay? CO2, we're looking for two things. Remember to determine if it's a polar molecule or not. We're looking to see if there's lone pairs and if the ends are the same or if the ends are different. So in CO2, there's no lone pairs and both of the ends are oxygen, so that means this is a non-polar molecule. So this would not experience dipole-dipole interactions. CO2, because it's non-polar, would exhibit what kind of forces? What kind of IMFs? It would exhibit an LDF. All right, let's look at the PF3. The PF3, right off the bat, I see these lone pairs here. The fact that it has lone pairs makes this a polar molecule. Because it's a polar molecule, it would exhibit dipole-dipole interactions between this PF3 and another PF3 if I were to draw it. SO3, let's take a look at the SO3 down here. I can see that there's no lone pairs around the central atom, and I can see that all of the ends are oxygen. That makes this a non-polar molecule. So would the SO3 have dipole-dipole interactions? No, because it's a nonpolar molecule. What kind of IMFs, intermolecular forces, would exist between two SO3 molecules? That would be your LDFs, not dipole-dipole. And then let's take a look up here at the CH3Cl. When we look up there, we've got no lone pairs, but there's different ends. So because there's different ends, that would be a polar molecule. And because it's polar, you would expect to see dipole-dipole interactions, okay? Let's take a look at this example. Which of these would experience dipole-dipole interactions? So again, pause if you need to practice drawing. If not, I'm just going to pop these up here really quick. Remember, the hydrogens don't get dots. The SO2 we drew yesterday. And the SiS2. So why don't you pause this, practice if you can figure out which one is polar or non-polar, and then which one's going to have the dipole-dipole interactions and which ones aren't, and then restart the video and see if you were correct. All right, so HCN, I can see that there are different ends. One end is hydrogen and one end is nitrogen. So this is a polar molecule. Let me switch my color here. And so that would have dipole-dipole interactions. Let's take a look at the CH2Cl2. Again, there's no lone pairs on that central atom, but there's different ends. So that is a polar molecule. So that would have dipole-dipole interactions. What about the SO2? I look at the SO2. I see those lone pairs right here. That means that this is a polar molecule. So that would have dipole-dipole interactions. What about the SiS2? I see there's no lone pairs on the silicone. I see that both ends are sulfurs. So that means this is a nonpolar molecule. And would nonpolar molecules exhibit dipole-dipole interactions? No, they would have London dispersion forces. So that my answers would be A, B, and C. The last type of IMFs that can be found between two covalent molecules is called hydrogen bonding. Okay. Now, in order to exhibit hydrogen bonding, the molecule itself would have to have a hydrogen atom, have to have a hydrogen atom, and the hydrogen would have to be bonded to a nitrogen, oxygen, or fluorine. And why does it have to be bonded to that? Well, because these have a high electronegativity, and it can create a really strong dipole. So a hydrogen bond is like a dipole-dipole interaction, but it's a really strong dipole-dipole interaction. Okay, now here's the thing. We've got our water example down here, and a hydrogen bond is not this right here where the oxygen is bonded to the hydrogen in the molecule. This is an intramolecular force because it's a bond. Hydrogen bonds are not the same thing as covalent bonds. A hydrogen bond is not a bond at all. It's an intermolecular force, okay? So this dashed line here represents your intermolecular force because it exists between two water molecules. That's why this one is the hydrogen bond, because it exists between those two water molecules, not in the water molecule itself. Now, you can easily recognize by looking at a formula whether or not it would have hydrogen bonding or not, because you can look at a formula and see if the hydrogen is bonded to a nitrogen, oxygen, or fluorine. So of these here, which of these would experience hydrogen bonding? Well, which has a hydrogen bonded to a nitrogen, oxygen, and fluorine? That would be your letter A. When you look at this example, we're trying to see which is incapable of forming hydrogen bonds. So you can look at these complicated formulas like A and C and wonder, well, how the heck am I going to draw this? What is this going to look like? Well, you don't really have to worry about it, because I can look at that H2 and NH2 and see the nitrogen and hydrogen together, see that that would actually have the capability of forming hydrogen bonds with another H2 and NH2 molecule. So I know that one has, well, let me not circle that because it says incapable of forming hydrogen bonds. This one is capable of forming hydrogen bonds. Letter B is methane. Is that capable of forming hydrogen bonds? No, because it has a hydrogen, but it doesn't have a nitrogen, oxygen, or fluorine. What about letter C? When I look at letter C, CH3, CH3, OH, that OH tells me that it could form a hydrogen bond because the oxygen is next to the hydrogen. And then same thing for letter D, CH3, NH2. I see that NH2 right there, and that tells me that that could form hydrogen bonds. So that can't be my answer. So to recap, we've got our three intermolecular forces that exist between two covalent compounds. Okay, so again, it's between the two molecules. London dispersion forces is the weakest, and we abbreviate that as LDF, and that's going to be between nonpolar molecules. Dipole-dipole interactions are the next strongest, and they're going to exist between two polar molecules, okay? Because that is a permanent dipole. The nonpolar molecules can only have a temporary dipole. And then hydrogen bonding is between hydrogen and fun, fluorine, oxygen, and nitrogen. Okay, so when those two things are bonded together in a molecule, it creates this really strong dipole that can form a really strong dipole-dipole interaction with another nearby molecule. Okay? So the types of questions we can ask about this can get a little bit tricky to understand. So you really want to kind of look at what the question is asking. So number one, it says between a CO2 and another CO2 molecule. So this is talking between two molecules. So I know that this is talking about one of my intermolecular forces, which is either LDF, dipole-dipole interactions, or hydrogen bonds. This can't be hydrogen bonds because there's no hydrogen. So CO2 looks like this right here. Let me just draw it up here. So is this a polar or a nonpolar molecule? It's a nonpolar molecule. So since it's nonpolar, this number one would be referencing LDF. Number two, between the C and the H in a C2H6 molecule. So this is in a molecule. This is talking about then an intramolecular force. It's talking about a bond because it's talking about something in the molecule. Well, if it's C and H, remember that's one of the two nonpolar covalent bonds. The other one is if it's bonded to itself. Well, this is a nonpolar covalent bond. Okay, Ca2 plus and O2 minus and solid CaO. Well, this right here is a giveaway. That's showing me that these are ions, and ions can only be found in anionic bonds. Ca is a metal, O is a nonmetal, so that's got to be ionic bond. Oops, I don't know why it does that sometimes. Next, between the N and the H in a ammonia molecule. This is key right here, in a ammonia molecule. Don't fixate on the N and the H and think, oh my gosh, I'm talking about hydrogen bonding. It would be talking about hydrogen bonding if it was between two ammonia molecules, but this is talking about just in the one ammonia molecule. That's why this is a polar covalent bond. Number 5, between an HF and another HF molecule. So keywords here, between and another, that's talking about two HF molecules. And because it's an H bonded to an F, and you're talking about another H bonded to an F, that's going to be your hydrogen bonding right here. Okay, and then between an NBr3 and another NBr3, so here we've got two molecules again. We're looking for those keywords. We've got two molecules. So what does NBr3 look like? Well, it looks like this. Let me just toss this up here really quick. Sorry, it's a terrible little drawing here. So NBr3 looks like this. What does this right here tell us? It tells us that that is a polar molecule. Since it's a polar molecule, we would expect to see dipole-dipole interactions. And then last question, intermolecular forces between molecules of SiH4. So now it's again talking about an intermolecular force, so that's got to be LDF, dipole-dipole, or hydrogen bonds. We know it's not hydrogen bond because there's no nitrogen, oxygen, and fluorine. So if we draw this here really quick, we see that all of the ends are the same. There's no lone pairs on that silicone. So this would have to be LDF, just like number 1. So here it says, for each pair, predict which substance would have the higher IMF with the molecule of itself. So again, you're trying to decide whether or not something is going to be polar or non-polar, okay? If it's polar, it would have dipole-dipole interactions or hydrogen bonding. If it's non-polar, it would have LDFs. Well, I can look at something like I2 really quick and see that that is going to be something bonded to itself. So that would be non-polar, which means this has to be LDF. I can look at HI, something like that really quick, and see that it would be an H bonded to an I. So this would be polar, which means that it would have dipole-dipole interaction. So of those two dipole-dipole interactions in London dispersion forces, which one is stronger? The HI. We've already drawn CO2 a couple of times, so I know that this is going to be nonpolar, which means it's LDF. OF2, I can draw this one really quick. It looks like this. And as soon as I draw it and I see these things here, those lone pairs on the oxygen, I know that this is going to be polar, which means it has dipole-dipole interactions. So I know this is going to be stronger because dipole-dipole is stronger than LDF. Methane or ammonia? Well, methane is CH4 and ammonia is NH3. So guess what? I don't even have to draw any of these to know what the answer is. I can see CH4. Remember, I told you all yesterday, you can look at something like that and you can visualize that it's one carbon with 4 hydrogens all the way around it. So it's going to be the same, which means that this is going to have LDF forces. And I can see NH. The N and the H automatically tells me that 2 ammonia molecules that exhibit hydrogen bonding. So this one is going to be stronger because hydrogen bonding is the strongest intermolecular force between covalent molecules. So I get to this next one, CH3Cl or CF4. I don't have to draw this CH3Cl to know that it's going to be polar. Oops. And how do I know it's polar? Because it's a carbon, and there's going to be 3 hydrogens and a chlorine, which means it's going to have different ends. So this would have dipole-dipole interactions between 2 CH3Cl molecules. I don't have to draw CF4. I can look at CF4 and I can see that it's going to be the same all the way around that carbon, all fluorines. So that's going to be nonpolar, and that means it's going to be LDF. So the strongest would be this one. Neon or xenon? Now, you might again be thinking to yourself, Miss Welch, this is just one thing. It's just one atom. It's just neon. It's just xenon. How can it have intermolecular forces? Well, if those atoms get close enough together, they can form an attractive force with another neon atom or another xenon atom. So remember, these would both be experiencing just the London dispersion forces because it would be a temporary attraction with another neon atom or another xenon atom. And what did we say can compare to London dispersion forces? More molecules. So since the xenon has more molecules, not more molecules, more electrons. Since the xenon has more electrons, it would have a stronger LDF, okay? Now, we've drawn both of these before. We know that PF3 has a lone pair on the P, so that means that this is polar, which means that this is dipole-dipole with another PF3 molecule. I've drawn the SiS2 before. Let me just draw it up here really quick again for you. This is what it looks like. Okay, there's no lone pairs on the silicone. The ends are the same. This is nonpolar. It would have LDF forces between 2 SiS2 molecules. So my answer would be the PF3. Okay, so that's your intermolecular forces. Give it a try. Let me know when you come back if you have any questions about the material. Okay?